Electric motors make almost everybody's job easier, from the hairdresser who depends on a small motor to keep a dryer running, to the engineer who relies on a much larger one to drive a locomotive down the track. It doesn't much matter whether they're large or small. Motors make work easier and save time, and so people rely on them. And here in the plant, when a motor breaks down, they rely on you. It's your job to maintain the motors in the plant, and you're the one they look to when motors fail. Now, to do that, you really got to understand what makes a motor go, and that's what we're going to concentrate on here. Now, you know that electric motors can be divided into two major classes, AC and DC. In this unit, we're going to go into the facts about DC motors pretty thoroughly. Now, we'll explain how they work, and then we'll go over the functions of each part of a typical DC motor. And then we'll talk about DC motor maintenance. And by the time we're through, you'll understand what makes a motor go, and you'll be able to identify several different types of motors as well. Now, a good place to start is with what makes a motor turn. And to do that, we have to go back a bit to review what you know about electromagnetic induction. Now, you know that a current-carrying conductor has a magnetic field around it. And you know about attraction and repulsion caused by magnetic fields. If I placed a conductor in a magnetic field and applied a voltage to it, the conductor would move right out again. That movement's motor action. Now, we're going to set up what's called an elementary motor, so you can see that movement clearly. You need to understand motor action to know why a motor turns. These two permanent magnetic poles produce magnetic lines of flux that extend from the North Pole to the South Pole. This is the main magnetic field. Between these poles, we'll add a loop of wire to act as a conductor. Now, if we were to wire the ends of the conductor directly to a DC power supply and apply voltage, the conductor would turn, but only as far as the wires would allow. So we need a better way to make a connection between the motor and the voltage source. These parts here will do the job. These are commutator segments, and these are brushes. These commutator segments actually come from a copper ring that was cut in half. We attach one segment to each end of the conductor, so they'll turn with it. We're going to use the brushes as the link between the power supply and the segments on the conductor. These are made of a carbon material that's similar to the lead in a pencil. These brushes don't move. The commutator segments slide against them as they turn. Okay, let's apply a voltage to the conductor and see how motor action works. You realize that as soon as current flows through this conductor, a magnetic field builds up around it. So now we have two magnetic fields. The main field located between the poles reacts to the field around the conductor. So the conductor rotates out of the main magnetic field. As you can see in this cross-section view, the conductor's magnetic field caused the lines of flux in the permanent magnetic field to shift. You can see that the direction of the shift is opposite from the direction in which the conductor is turning. And by the way, the rotating assembly of any DC motor is always called the armature. Now, since it's the action of the rotating conductor that causes the shift in the main flux field, the shift is called armature reaction. This reaction causes a shift in what's called the neutral plane of a motor. Now, the neutral plane's important. It's the point where there's no current flow through the conductor. This is how the main magnetic field looks when there's no voltage applied to the conductor. The position of the neutral plane is here. Now, when voltage is applied to the conductor, the magnetic field shifts, so the position of the neutral plane is now here. So it's the place at which the brushes in the motor can short the conductor without doing any damage. Shorting the conductor when it has current flowing through it will cause sparking. The heat from the sparks could damage the commutator segments. To prevent this from happening, you must compensate for shift in the neutral plane. Now, one way of doing this is to move the brushes against the direction of the rotation until you find the new position. That would take care of the problem, but it's not a practical solution. You see, the neutral plane shifts each time the load on the motor changes. If you use this approach, you'd have to adjust the position of the brushes with each change in load, and, well, that's next to impossible. Now, look at this end view of our conductor and the main magnetic field. Current flow goes into the conductor here at the cross or back of the arrow, and out here at the point of the arrow. Now, the smaller the load, the less current there is flowing through the conductor. That means there's a smaller field around the conductor, too. So the shift in the main field would be less. As the load gets heavier, more current flows through the conductor, and it has a bigger field around it. So it causes a greater shift in the main field. Since it's not practical to adjust brushes with every load change, most DC motors have small poles like this installed between the main poles. These small poles are called interpoles. They're used to prevent the main field from shifting too much with each load change. In effect, they keep the neutral plane in place. They're set up between the main field poles. They're connected so that the polarity of each interpole is the same as the polarity of the field pole that precedes it, according to the way the motor turns. The other thing to keep in mind is that the interpoles are always connected in series with the conductors. So, since current's always constant in a series circuit, if there's a change in the field around the conductors, the same change occurs in the field around the interpoles. The end result is that the magnetic field around the interpoles opposes any change in the shift of the main magnetic field, regardless of load change on the motor, and the problem with the neutral plane is solved for all practical purposes. Now, there's one other aspect of motor operation that we ought to cover before we go on. That's counter-electromotive force, or counter-EMF, CEMF for short. You should know that when a current-carrying conductor moves in a magnetic field, a voltage is induced in that conductor. The amount of voltage, EMF, induced depends on three factors: the strength of the magnetic field, the number of current-carrying conductors, and the speed of the motion. The EMF, the applied voltage, is produced by an outside source, but the CEMF is produced within the motor. When a conductor first begins to rotate, the CEMF is very small, but as the conductor builds up speed, the CEMF increases too until it almost equals the applied voltage. Now, the actual amount of difference between the applied EMF and the CEMF is important. It's what controls the current flow through the armature. Well, we've covered two key points on motor action: how the position of the neutral plane is established and the effect of CEMF. And that's about all we have to say about why a motor turns. So let's go on to examine a typical DC motor. This example is a compound motor. We've disassembled it here to make it easier to see the parts. This is the yoke, but most of the time it's called a frame. It supports all the other motor parts. It also forms part of the motor's magnetic circuit. The magnetic circuit is the path that the magnetic field follows through the motor frame. Usually, the frame is the part that's used to mount the motor on the foundation. These are the field pole pieces. They support the field coils, and they're bolted to the frame so they can be removed if you need to replace or repair the coils. The main field poles are made up of the field pole pieces and the field coils. Together, they provide the main magnetic field in the motor. We're just going to mention them here because later we'll go into specific details about them. This large winding is the shunt field coil. The smaller winding here is the series field coil. This small pole piece with the coil around it is an interpole. It's bolted to the frame so it can be removed too. These interpoles help to compensate for armature reaction. These are the end bells. They support the brush rigging and the inspection covers, and they house the bearings which support the armature. The end bells are bolted to the frame so they can be removed when you need to make repairs to the motor. This is the brush rigging. It supports the brush holders. This is a brush holder. It holds the brush and the brush tensioning assembly and provides a connection point for the brush and the field coil. The brush tensioning device is what holds the brush securely against the commutator. The brushes make the sliding electrical connection with the commutator and provide the path for current. This is the brush pigtail. It's attached to the brush holder. The armature here is the entire rotating assembly. It's made up of the shaft, the armature core, the armature windings, and the commutator. The shaft supports the armature and allows it to turn. The core supports and houses the armature windings. These windings are the rotating, current-carrying conductors, and the commutator is the electrical connection that goes from the brushes to the windings. The actual connections to the windings are here on this section of the commutator. These points are called risers. Well, we've talked about motor action, and we've looked at the parts of a typical DC motor. There's a diagram of this motor in your text. Why don't you take a few minutes to look it over and make sure you understand the function of each part. There are several types of DC motors. Identifying the type you're working with isn't hard if you know what to look for, and you do need to know. Otherwise, you'll waste a lot of time. And you stand a good chance of damaging the equipment if you start looking for a problem before identifying what type of DC motor you've got on the bench. The methods used to troubleshoot a DC motor or to test it depend on what type it is. Now, we're going to use diagrams or schematics of motors to show you how to identify them. DC motors are classified in a number of ways, but the most common way is according to what type of field winding they've got and the way their fields are connected. This is an illustration of a series motor. It's about the simplest kind of motor you'll come across. The field coils, which we call the series field, and the armature are connected in series with each other, and there's only one path for current flow. This is a simple schematic diagram of the same motor. You're going to be using this type of diagram when you start working on DC motors. As you can see, the series field and the armature are in series with each other. The markings that you see here are standard for DC motors. They're your best guide to what type of motor it is. The series field is marked S1 and S2, and the armature is marked A1 and A2. The numbers indicate the direction of current flow, from the smaller number to the larger one. Now, a word of caution concerning series motors is necessary at this point. Because of their construction, series motors can overspeed to dangerous levels if they're run without a load. The series field of this type of motor is made of a few turns of large wire, and its resistance is very low. When it's connected in series with the armature, whose resistance is also very low, current flow through the motor is very high. The magnetic fields of both the series field and the armature are very strong, and there's very rapid motor action. Now, this motor could run away and tear itself apart, so you never, and I mean never, start a series motor unless it's connected to a load. This is an illustration of a shunt motor. The standard marking for the shunt field is F. Now, you can see the markings F1 and F2 for the shunt field. This diagram shows that the field coils and the armature are in parallel with each other, and there are two paths for current flow. Now, there are a couple of facts about shunt motors that you've got to be aware of. First of all, the coils in the shunt field are made of many turns of fine wire, so its resistance is high. Secondly, the resistance of the armature is very low, maybe as low as 1/2 an ohm. If you applied full-line voltage to this motor, you could wreck the armature. It just couldn't handle the high current flow. To avoid this, you must install resistance in series with the armature before you start it. This is an illustration of a compound motor. It's more complex than the two we've just seen, and it's probably the type you'll come across most often. Looking at this diagram, you can see it has a series field that's connected in series with the armature, and a shunt field connected in parallel with the armature. Notice the field and armature markings. They tell the story. Now, when you're working on a compound motor, the thing to keep in mind is organization. You've got to make sure each lead is marked so you won't make any mistakes when you're reconnecting the motor. And you've got to double check each connection you make to be sure it's right. Oh, one other thing. Bear in mind that if you open the shunt field, then what you've got on your hands is a series motor and all the dangers that go along with it. If there's a manual available for the motor, one glance at the schematic will tell you immediately what type of motor it is. Now, you can see what I mean here. In this diagram, the markings on the fields immediately identify it as a series motor. The same is true of this diagram. The F markings identify it as a shunt motor. The fact that both types of markings are present in this one makes it obvious that it's a compound motor. Now, if the manual for the motor's been lost, you've still got some other options left. The easiest is to look on the motor nameplate. Under the block that says wound, it'll say either series, shunt, or compound. If the nameplate's missing, then you've got to go by the motor lead markings. Remember, we said that the armature leads are marked A, the series field is marked S, and the shunt field is marked F. If your motor leads have all three markings on them, it's compound. If the leads are marked A and S, you've got a series. It's a shunt if the leads are marked A and F. Well, we've covered a lot of information in a relatively short period of time. Why don't you take some time now to look over the material in your text on how to identify a motor using a diagram and answer the questions you'll find there. If you have any questions, be sure to clear them up with your instructor before we go on. You're going to see bearings and field windings fail in all types of motors. It's just the way it goes. But with DC motors, you'll also find that you'll be dealing with a set of problems that crop up because of the way they're constructed. Now, I'm not saying you can do anything about the way they're built, but you can minimize the problems that arise from their construction by observing good maintenance practices. We're going to go over three major sources of problems in DC motors: brushes, brush riggings, and commutators. We'll cover brushes and brush riggings in this segment, and we'll go over commutator maintenance in the next. We have this motor in the shop, and we'll use it to demonstrate good maintenance practices. If you are to make repairs in place, you must follow the plant's tag-out procedures and verify electrical isolation before you start work. This is a compound DC motor. We'll mention the kinds of problems you'll be running across first, and then go on to cover what you can do about them. Let's start with the commonest source of trouble, and the one that's easiest to correct: the brush. As the brush slides on the commutator, it's going to wear, and as it does, carbon dust from the brush will cover other parts of the motor. That leads to problems. Any brush is going to wear down eventually. You've got to replace them when they get too short to do the job. Brushes can hang up in their holders and break contact with the commutator, or the pigtail can bind on the holder. That will cause the brush to break contact too. You've also got a problem if the brush doesn't make full contact with the commutator. If the brush tension device is set wrong, there'll be trouble. Broken, cracked, or chipped brushes will also give you headaches. You see, the size of the brush is determined by how much current it has to carry. Cracks or chips reduce the surface area of the brush, so current has a smaller area to go through, and this causes sparking, arcing, and heats up the brushes. The same problems occur if the brushes aren't making full flat contact with the commutator. Sparking at the brushes is an almost certain indication of commutator problems. Sparking can be minor, or it can be extreme, with what looks like fire completely around the commutator. If there's sparking at the brushes, it's a sure sign of potential problems. The first thing you ought to do is check to see if the motor's clean. In fact, cleaning the motor thoroughly is the first order of business in any maintenance procedure, and we'll start doing that now. Then we'll inspect each part as we go along for the problems we just mentioned. Open the inspection covers and vacuum the interior of the motor as thoroughly as you can. Then take an approved cleaning solvent and some clean rags and wipe out the interior. Be sure you observe the safety precautions established in your plant for using cleaning solvents. Pay particular attention to the brush holders and the brush rigging, and be sure to clean the commutator thoroughly. Make sure you get the area between the segments too. Be very careful when you're using solvents on the commutator though. Do not remove the brown coating from the commutator segments. That's there for a reason, and we'll talk more about it later. Now, this is what a good brush looks like. The sliding surface is smooth and shiny, and it conforms exactly with the shape of the commutator. It's making 100% contact. There aren't any chips or cracks in it, and it's not too worn. A good rule of thumb is to replace the brush when it's worn down to 1/4 of its original length. The pigtail still securely fastened to the carbon. It's flexible, and it isn't frayed or discolored from overheating. So this brush can be reused. All the other brushes have to pass this checklist too. If the brush doesn't meet each of the requirements, replace it. All right, next we'll look at the brush holders. The insides should be clean and smooth. If there are burrs or dings inside, the brush might get hung up on them, and then it won't make good solid contact with the commutator. These bottom edges should be smooth, straight, and free of burns. Now, most brush holders can be moved, so making sure they're properly adjusted is essential. What you adjust is the amount of distance between the bottom of the holder and the surface of the commutator. Always check to see that the space between them is correct. If the rigging's too high, the brushes will chatter and make a hissing sound, or the brush could lock in the holder and break contact with the commutator. The brush could also get hung up and break off. Too close to the commutator surface isn't any good either. Now, for one thing, it increases the danger of arcing from the commutator to the rigging. The brush holder's usually made of metal, so it's a better conductor than a carbon brush, and current is always going to follow the easiest path it can find. Check the motor's manual to find out exactly what the distance should be and set it accordingly. If the information's not available, a good rule of thumb is to set it between 1/16 and 3/16 of an inch from the surface. Using the metric system, it would be 1.6 to 4.8 millimeters from the surface. The other thing you might have to do is adjust the stagger of the rigging so that the brushes cover almost the entire surface of the commutator. To do that, you loosen the brush holder bolts and move them so that the brushes cover as much area as possible. Make sure you always stagger the brushes in positive and negative pairs. Otherwise, negative brushes will track each other and wear unevenly. And by the way, those are general rules for staggering, but it's not always necessary to stagger the rigging on every motor. For instance, you don't stagger the brushes on a 2-pole motor. And if the commutator that the brushes are riding against shows signs of wear, like this, then you wouldn't want to stagger these brushes. You can see why. The brushes and the commutator have formed wear patterns. If you move the brushes, they won't make full contact with the commutator. Instead, you should inform the foreman that both the brushes and the commutator are going to need attention. When you're sure the rigging's in place just right, you can reinstall the brushes. If a brush needs to be replaced, make sure the one you put in is the right type and grade for the motor. Now, in some plants, all new brushes must be seated. Follow your plant's procedure if there is one. You can seat a brush a number of ways. Since this is a small motor, we're going to use some extra fine flint paper to do it. If you decide to use this method, bear one thing in mind. Don't try to substitute emery cloth or emery paper for flint paper on a DC motor. or you'll regret it. You see, emery particles are conductors. If they find their way into the area between the commutator segments, they'll short the motor. Okay? First, you tear a strip from a sheet of flint paper. The strip of flint paper must be at least as wide as the brush to be sure the entire surface is seated. Now place the flint paper on the commutator flint side out. Then replace the brush and set the tensioning device to hold the brush tightly against the flint paper. Rotate the armature slowly in the direction of motor rotation until the flint paper is out from under the brush. Then remove and inspect the brush. Repeat the procedure until the contact surface of the brush has the same shape as the surface of the commutator. When you've got 100% contact, the job's done. Be sure you remove any carbon dust in the motor afterward. All right. At this point, your brushes are ready. Your motor is clean, and you can begin to reinstall the brushes. Start by moving the brushes up and down in the holder to make sure they're not hung up somewhere. Then set the tension devices. If there's no pressure setting given in the manual, well, a good rule of thumb is 1 1/2 to 2 pounds pressure per square inch of brush seating surface. If the manual has disappeared, well, you could figure it out mathematically. After you've found out what it ought to be, you can use a brush tensioning scale. Attach the scale to the tensioning arm and pull until the brush just clears the commutator. Then read the scale. Adjust the tensioning device until you have the correct pressure. Now connect the brush pigtail to the brush rigging and make sure the connection's tight. We've covered brushes and brush problems pretty thoroughly here. Why don't you take some time to look over the information in your text now and answer the questions you'll find there. Well, we're going to look at the second major source of difficulty with DC motors now, the commutator. Commutator problems are fairly easy to see, but they're much harder to correct than most of the problems we just looked at. After we've gone over some of the things that can go wrong with the commutator, you'll come to see that many times they're the result of brush problems. Before we go into specifics on commutator problems, there are a couple of things you can do that will help to keep them down to a minimum. The first is to keep the motor clean, and the second is to take care of brush problems as soon as you become aware of them. Now this commutator is looking good. Its surface is smooth and highly polished, and it's got good color. Good color ranges from light brown to chocolate. It's due to a self-generated film that aids commutation, and that's why we said to be careful not to take the finish off the surface when you're cleaning it up. You can use a canvas wiper to do the job. It's just a piece of canvas fixed to a wooden handle. The canvas is sturdy enough to clean the surface without removing the film. Don't neglect this area between the commutator segments. It's likely to collect carbon dust, brush chips, copper flakes, and other particles. It's not difficult to check. With a good light, you should be able to see whether or not the mica that insulates the copper segments from each other is okay. If the mica is clean, its color will be anywhere from light gray to white. If it isn't, dirt and other particles will show up as dark specks. Now, you can do a pretty good cleanup job with a soft brush. Most of the time, a hand slotter and scraper is used to remove any particles that get stuck between the bar. Dry air is good for cleaning away the debris between the segments. Before you put the brush and air hose away, there are two other areas you should check thoroughly: the bearing end of the commutator and the area behind the risers for carbon dust and dirt. These areas are susceptible to grounding. We're going to show you some illustrations of damaged commutators, and we'll go over what happened to them and how it can be prevented. Before we do, though, there's one thing you should bear in mind. What looks like major damage to you may not look the same way to your supervisor. It's important to report all damage or suspected damage on the commutator. But before you do any corrective maintenance, get your foreman's okay. We're going to look at evidence of two typical problems: threading and grooving. This commutator's threaded. See these fine lines cutting into the surface here? They look as if they're machined in. Copper is being transferred from the commutator to the brush. You'd find copper flakes embedded on the seating surface of the brush when you inspected it. Threading causes the brushes to wear rapidly. It's often caused by low brush pressure, contamination, or the wrong type of brush. Now, minor threading won't really interfere with the operation of the motor, so your foreman may just decide to let it be. You can prevent further damage from threading, however, by cleaning the commutator thoroughly, cleaning the seating surface of the brushes, and correcting the brush tension. If the problem occurred because the wrong type of brush was installed in the first place, replace it, making sure you've got the right type and the right grade of carbon. If you're not sure what's required, check the manual or ask your foreman to advise you. This condition's called grooving. See the smooth slotted area on this commutator? It could be caused by an abrasive brush or by contamination. Now, any brush causes a certain amount of wear on the commutator, but an abrasive brush causes excessive rapid wearing. If you see grooving, it might be because the brush is built wrong, or it could have impurities in it. You'll also find that using the wrong type or grade of brush will cause grooving. Again, grooving won't necessarily interfere with the operation of the motor, but if you find evidence of it, you should clean the commutator carefully and replace the brush. What we're going to look at next is an indication of copper drag. These copper flakes that you see at the trailing edge of the commutator could be an early warning of trouble. If enough flakes accumulate, they'll close the space between the commutator segments, and then you've got flashover to deal with. We'll say more about flashover in a minute. But before we do, let's go over what causes copper drag. Now, it's usually one of three things. The pressure on the brushes might be too light, or there may be some excessive vibration, or you might have an abrasive brush. If you see any sign of copper drag, make sure you clean the commutator thoroughly and remove all the buildup between the segments. Check to make sure the brush is right and readjust the pressure on the tensioning device. And by the way, you may wonder why we didn't go into what you can do to correct any damage that had already been done to the commutator. Well, it's because that decision is usually up to the shop foreman, and he'll tell you what corrective action he wants you to take. We used the term flashover a minute ago. Now, let's go into what it is, what causes it, and how to prevent it. Flashover is a short circuit between the brushes of the motor. Current follows a path through the air and over the surface of the commutator. In any short circuit, there's very little resistance and extremely high current flow, which in turn produces intense heat. That heat can do major damage to the motor. In fact, most equipment has overcurrent protection that cuts off the motor if flashover occurs. Now, although flashover occurs quickly, the elements that cause it build up slowly. Dirt, carbon dust, or copper flakes on the surface of the commutator, between the segments, and on the brush rigging, all combine to create the circumstances in which it can occur. What actually happens during flashover goes something like this. Dirt between two segments of a commutator might cause them to short together. This produces sparks or arcing, depending on the severity of the short. If the arc generates enough heat, the air becomes a conductor. And as you can see here, current follows the path of least resistance, from the negative brush through the heated air to the positive brush. Anytime you've got air hot enough to act as a conductor, you'll have flashover. Extreme overload also causes sparking or arcing intense enough to heat the air to the point where it becomes a conductor. If the motor is suddenly heavily loaded, the motor speed drops, counter EMF decreases, and current flow increases through the armature circuit. High current flow through the brush and the commutator can cause sparks or arcs that heat the air enough to cause it to conduct. And then you've got the elements of flashover again. Loss of brush contact sets the same operation in motion. When the brush comes off or loses contact with the commutator, sparks or arcs will occur between the brush and the commutator. Again, they may heat the air hot enough to cause it to conduct, and then flashover occurs. The results of flashover can be very severe. Melted brush pigtails, burned brush holders, charred brush rigging insulation, and burned brushes can all happen in a flash. In addition, the commutator is likely to be severely damaged. You may have to replace and seat all the brushes and replace or at least clean and dress up all the brush holders. The brush rigging may have to be replaced or at least cleaned. Now bear in mind that you have the ingredients for another flashover if you don't remove all charred material from the motor completely. Charred insulating material is a conductor. Any charred paint has to be completely removed for the same reason. All that work and expense could be prevented most of the time if you do your job well. Preventive maintenance performed periodically and thoroughly will prevent flashover. Well, by now you might think cleanliness is heavy on our minds. Well, you're right. Dirt and other types of contamination are electrical equipment's #1 enemy. We stress cleanliness because it's very important. Now, before we go on to troubleshooting, why don't you take some time to review the material we've just covered in your text. If you've got any questions, now's the time to clear them up with your instructor. Well, suppose the brushes and the commutator are all checked out and you've still got a problem. Your next best bet would be to check the armature and field, both the windings and their connections. What you want to look for specifically are grounds, opens, and shorts. These are all troubles that may affect an electric motor from time to time. To demonstrate how to locate these problems, we're going to use a motor, a simple diagram, and a megometer. Okay, whenever you're troubleshooting, you start by identifying the problem. What we're going to look for is a ground, a breakdown in insulation that provides a current path to ground where there shouldn't be one. This diagram shows us what we need to know about the motor to look for a ground. As you can see, all the windings, including the armature, are connected together. So, if we connect the ground lead from the meter to a metal section of the motor and the line lead to the motor leads, we'll have a current path to ground, provided that the motor is grounded. All right, let's check. Well, this motor is grounded. If all you had to do was report whether or not the motor was grounded, you could say yes and be done. But if you had to repair it, then you'd have to locate the grounded part or parts. There's no guarantee. There's only one. Here's where you use the process of elimination to save you time and prevent unnecessary confusion and error. To go any further, you have to break the circuit up and test one part at a time, eliminating the parts that are good so you can work on the ones that are causing the problem. According to the diagram, the ground could be in any of three circuits: the armature, the series field, or the shunt field. You can see what happens if we raise the brushes off the armature. We've got three separate circuits that can be tested individually. Let's check the series field first. You know that the standard marking for the series field is S, so that's what we look for. Okay, here's the lead we want. Now we can check the field. Nope, the ground's not here. Let's go on to the shunt field. This time, the lead's marked F. Okay, here it is, and yes, it's grounded. But we're not finished. We've only found one ground. The armature might be grounded too, for all we know. and you've got to eliminate all possibilities before you begin the repair. To check the armature, we'll move the ground lead to the shaft to be sure we get a true reading, and then touch the line lead to the commutator. The armature reads good. All right, now we've totally eliminated the series field and the armature from consideration as far as the ground is concerned. Your next move at this point would be to disassemble the motor. To determine which field coil the ground's in, we have to break some connections. By breaking up the circuit and testing one section at a time, we can continue the elimination process. First, let's break the connections here between the field coils. Okay, it's grounded. We've got to check the other coils too to see if they're also grounded. No, they're okay. Now, to determine which one of these field coils is grounded, we must break this circuit. We'll break this connection. Okay, let's check each coil. Let's check this one first. This one's grounded. Now let's check the other one. It's okay. Now we've eliminated every single part of the motor except this shunt field coil. That's the only way to do it, regardless of what kind of problem you're dealing with. Divide and conquer is a good strategy for you to use. To put the motor back in service, all you'd have to do is unbolt the pole piece, replace the bad coil, and reassemble it. But suppose the trouble was actually caused by an open, a break somewhere in a circuit that stopped current flow. Well, you'd proceed differently. You'd use an ohmmeter, and you'd check each circuit individually from end to end. And that's exactly what we're going to do. Here's the diagram. As you can see, there are two paths for current flow. We have to break them up in order to check the circuits one by one. Lifting the brushes off the commutator gives us 3 individual circuits again. This time, we'll do the shunt field first. The diagram shows us we have to read through the shunt field from F1 to F2. So we need to locate these 2 leads in the motor. Here's F1 and here's F2. But it's got A2 on it. That would be a problem if we hadn't lifted the brushes off the commutator. But since we did, we took out the armature circuit. So we can be sure we're reading only the shunt field. Okay? With 1 ohmmeter lead on the shunt field lead, F1, and the other on the shunt field lead, F2, we should get a reading. And we do. That means the shunt field's not open. Next, we'll check the series field. The motor leads for this field would be marked S1 and S2. Here's S1, but S2 is not so easy to find. A look at the diagram shows that S2 is connected to the brushes. Which brush is the question? The easiest way to find out is to put 1 ohmmeter lead on S1 and take the other to the lead connections on the brush holder and see if we get a reading. Nope, nothing. That means one of 2 things. Either we're reading the wrong brush holder or the series field's open. Let's change the lead to the other holder. Okay, we do get a reading here. That means we're on the right brush holder and that the series field is not part of our problem. Did you notice the difference in the readings? High reading for the shunt field and low reading for the series field, just as we should get. But we aren't completely through with the series circuit yet. If you think back, you'll realize why. We only eliminated part of the series circuit, up as far as the brushes. We said these brushes can be trouble spots in a DC motor, and it's true. You'll find that they're worth checking. We'll go back to the holder where we didn't get a reading and continue. Let's put the brush back and reset the tension. Okay, now if we place 1 ohmmeter lead on the pigtail and the other on the commutator segment just under the brush, we should get a reading. Let's check the diagram first to be sure there's no other path for current flow. There isn't. Okay, what does the dial read? Nothing. There's an open here. Okay, now we have to repeat this brush check again on the other side. It's probably still okay. All right, the brush is back. The tension's adjusted. Yes, we've got a reading here. Well, we've got to do a more detailed check on the questionable brush. The procedure is check its length, pigtail, contact surface. Then the inside of the holder to see if there are burrs or bends. The bottom is smooth, no burn spots. Then check the commutator. It looks good. According to what we've seen, there's no reason why the brush, the holder, or the commutator shouldn't be okay. Let's replace the brush in the holder and reset the tension device. Let's check this brush again the way we did before. Now we get a reading. All right, now let's test the whole series circuit. Here's the diagram again. If we put 1 meter lead on F2A2 and the other on S1, we'll be able to check to see if the armature, brushes, and series field are all right. We'll bypass the shunt field. So we're going from motor lead S1 through the series field to S2A1, through the brush, through the armature, and the other brush, to A2F2. Let's check this circuit. We're getting a reading. That means the series field, the armature, and the brushes are good. The trouble was in that brush, after all. Well, the last of the 3 problems we mentioned was a short. A short's just the opposite of an open. Instead of maximum resistance and no current flow, you will find evidence of minimum resistance and maximum current flow. Excess current generates heat in the damaged component, and it becomes apparent either a fuse blows or a breaker trips. You might have an operator come running, shouting that the motor's burning up because he saw smoke. Smoke or a blown fuse is a pretty good clue that you may have a short. If the equipment is a motor, it's good procedure to check it for grounds first, since shorted coils in a motor are highly likely to ground. If the test does not indicate a ground, then you're going to have to look for the short. The best tools you've got for locating a short are your eyes, nose, and hands. The insulation on a part that's shorted might be hot. It'll be charred and break and crumble when you touch it. You'll also notice a distinctive smell that lasts for hours. Oh, one last thing about shorts. They don't last long. If a fuse doesn't blow or the breaker doesn't trip, the short will quickly become an open. Don't waste your time looking for a short with test equipment. Your senses will tell you just as well. In fact, although meters and test equipment are sometimes essential problem-solving tools, it's a good idea to check for simple, obvious things first. Look for broken wires, loose screws, short brushes, and charred insulation. The more experienced you are, the more you'll learn to rely on your own observation first and test equipment second. Okay, let's stop here so you can take some time to look over the material in your text. If you have any questions about what's been covered so far, be sure you get them answered before we go on. As long as you're in this line of work, you're going to be tearing down motors and putting them back together again. Obviously, the better you're at it, the easier your job will be. We're going to go over how to disassemble a DC motor, then we'll inspect it and reassemble it. Anytime you're going to start a job, you have to make some preparations. In this case, you start by getting together all the tools you'll need. Oh, and have a couple of containers to put parts in so they won't get lost. If you're planning to replace any parts, make sure you've got the right ones ready before you start. Now, most of the procedures we'll follow apply to all types of electric motors, so it'll be worth your while to watch closely. You've got to remove the inspection covers so you can get to the brushes. Loosen the pigtail bolt and slip the pigtail out. Release the brush tensioning assembly and remove the brushes. It's best to put them in a separate container to protect them from damage. Then remove the field coil leads from the brush rigging. Next part is the end bells. Before you remove them, they have to be marked so you can get them back together right. Use a center punch and hammer to mark the end bells and the motor frame. After that's done, take a wrench and remove the end bell bolts and put them in the parts pan. Use a saw-faced hammer or a similar tool to knock the end bells loose from the frame. Getting the end bells to slide off the bearing can be a problem. You might have to use a couple of small pry bars to get them off. Be very careful when you've got them loose. You don't want the end bell to cock and cause the brush rigging to damage the commutator. After the end bells are off, you can remove the armature. Lay some rags across a workbench before you start so you'll have a place to put it. Don't drag it across the pole pieces. You might end up damaging the armature or the pole pieces or both. Lift the armature and move it out of the frame. Okay, now you can get to the bearings. We're using a bearing puller to get them off. Well, the motor's apart. The next step is to inspect it thoroughly and give the parts a good cleaning. We put the armature in a set of V-blocks so we can look it over. Look for evidence of the types of problems we went over earlier. Check the level of the insulating material between the segments. It should be about 1/32 of an inch below the level of the segments. Certainly not lower than 3/64 of an inch. If the level's too high, you'll have to undercut. And you can do it by hand or with a power tool specifically designed for this purpose. Inspect the armature windings. Look closely at the area where the windings connect to the risers. See if there's any evidence of solder being thrown out of the risers. Thrown solder's usually an indication that the commutator's overheating. It could mean that the motor's running overloaded or that you've got armature winding damage. We'll go over how to check for damage to the windings in just a moment. Check the armature banding to be sure it's tight and intact. Check the back of the coils for damage. Pay particular attention to the condition of the insulation. Okay, the next step is to thoroughly clean the entire assembly. Make certain you're using an approved solvent and following all the safety precautions required. Be sure to clean the area at the front of the commutator, behind the risers, and the back of the coil windings. After you've completed your inspection, thoroughly clean the armature and repaired any damage you found. Check it for shorts with a growler. A growler is a piece of test equipment that uses AC voltage and the principle of induction to do the job. When a voltage is induced in the windings, they set up magnetic poles in the armature. We use a hacksaw blade placed over the armature slots like this. If there's a short in one of the windings, you'll hear something like this. Be careful when you're doing this test. Because there's a voltage set up in the windings, you'll get quite a jolt if you brush against the commutator segments. Test for grounds next using a megameter. After that, you can be sure the armature's good and it's ready for the bearing. Now, we're going to use a press to reinstall these bearings. Then we're going to cover the assembly and set it aside so it won't be damaged while we continue the rest of the inspection. Next items on the list are the motor frame and the field poles. They've got to be cleaned real good first. Pay special attention to the area between the main poles and around the interpoles. Clean out all the dirt and carbon dust. Okay, now it's time to check the field coils. Carefully inspect them. Look out for cracked or broken insulation. Be sure to examine the interpoles too. Repair any damage to the insulation using the insulation varnish. Check the pole pieces for dents or burrs. Use a file to remove them. Then check all field coil connections and coil leads for damage. Check the insulation here as well for cracks or breaks and repair as needed. Check each connection for tightness. All right, now check the machine surface for burrs and dings. They've got to be removed. Use a wire brush to remove any dust and dirt. The entire surface should be smooth when you're finished. Okay, now you're ready to check the field coils for grounds with a megameter. After that, you can set the frame aside until it's time to reassemble. All right, the end bells are next. One at a time, check each one for surface burrs and dings and remove them. Then go over the entire surface with a wire brush. Carefully clean the entire end bell with the same solvent you used before, taking special care to do the bearing housing well. Set the end bell aside and do the other end bell the same way. All right, the brush rigging and brush holders get cleaned up next. Make sure you do a thorough job on the insulating parts on the rigging. Okay, now that the end bells and the rigging are clean, inspect them. We've already talked about inspecting the brush rigging at length, so I'll just mention the high points. Check the holder for bends and dings, the tensioning device for broken parts, and the pigtail connection screw. Then use the megometer to check the rigging for grounds. Okay, the last part is clean and inspect it, and we're ready to reassemble. First step is to carefully place the armature in the motor frame. Don't slide the armature on the pole pieces. Check your frame marks to be sure it's in right. End bells are next. Put on the one that's farthest from the commutator first. Line the bearing housing up with the bearing. Then tap the saw-faced hammer against the end bell until the bearing is in its housing. Before you line up the punch marks and start the end bell bolts, lubricate the bolt threads. Don't tighten the bolts yet, just start them so the end bell won't slip off the bearing. Then replace the other end bell. Be careful not to let the brush rigging hit the commutator. Use your soft hammer to tap the end bell on the bearing after you've lined it up. It won't go on all the way until you've lined the machine surface up with the frame. Now, align the end bell and the frame marks and install the second set of end bell bolts after they've been lubricated. Use the bolts as a guide to align the end bell and the frame machine surface and tap the end bell onto the frame. Be sure it goes on straight. The crack between the end bell and the frame should be the same size all around the motor. Using the right size wrench, run the bolts so they're just snug. Don't put any pressure on them yet. We just want the bolts to hold the end bell right here. Okay, we repeat the same drill with the other end bell. Align it to the frame, tap it in, and snug up the bolts. Now, let's tighten the end bells. To make sure they go on straight, we're going to tighten them slowly, one at a time, in a diagonal pattern across the shaft. A couple of turns on this one, now on this one. You continue the process until each end bell's tight. As you work, keep an eye on the crack between the end bell and the frame. Try to keep an even space all around. Adjust your tightening of the bolts to compensate if it seems to be uneven. All right, now do the other end bell the same way. Turn the shaft by hand. It should and must move freely. If this shaft doesn't spin freely, you must recheck your work. Be sure the end bells are on straight and the end bell bolts are tight. Now, if this all looks good, you may have a bad bearing. If this is the reason for the motor not turning freely, it will have to be taken apart again and the bad bearing replaced. Never start any electric motor unless the shaft is free to spin when turned by hand. Now, connect the field coil leads to the brush rigging. Make sure the connections are clean and tight. All right, now let's look at our brushes. Remember what we said about the condition of the brushes? Make sure they're not too short and free of chips and cracks. Their contact surface should be shiny and smooth. The pigtail shouldn't be frayed. They should be flexible and securely fastened to the carbon. Place the brush in the holder. Set the tensioning device. Use the scale to give you proper brush pressure. Then connect the pigtail to the rigging. Well, at this point, the motor's reconditioned and it should function normally. The last thing you've got to do before you take it out of the shop is to take a ground reading on it and check it for opens. Well, we covered a lot of ground here. You should be able to tackle just about any DC motor now. Troubleshoot it, disassemble it, repair it, and put it back online. The procedures we followed here should save you a lot of time and effort. If you've got any questions about anything we've mentioned, be sure to clear them up with your instructor.